We'll give people a couple more minutes before we start. So welcome to everybody. Well, welcome to everybody. I'm sure a couple more will show up, but we'll go ahead and get started. I'm Barney Ricca, and I've been doing some of these seminars for people as seems to be appropriate. Today, we're going to talk about catastrophes and catastrophe theory. And catastrophe theory is really used in two ways. One is it's a branch of topology, and it deals with things like the discontinuous and divergent phenomena that sometimes appear. It's also a way of exploring data that's often used to find out what's going on in data sets that seem to be a little bit inconsistent. And so one of the first things to note is if you have data where something's going on, but it doesn't seem to be consistent, it's entirely possible that catastrophe theory may help. It works with data where there are sudden changes in some output or some outcome, depending upon some small change in an input variable. We'll see a number of examples of these things as we go on, but it really is one of those things where sometimes you say your data are too noisy or they're too inconsistent or there's something like that. Oftentimes, catastrophe theory can provide a good analysis tool for these data. It can also help you generate theory where you're trying to figure out what's going on and come up with some way of describing this. So this is part of the Nonlinear Dynamics seminar series here at the Lyda Hill Institute. Nonlinear thinking is different than linear thinking. And so we're going to explore some of those things, some different ways of thinking about situations. How can nonlinear questions open up new questions? How can nonlinear approaches sort of help us understand the theory that we want to develop? These are not going to focus on how to do something, but rather why you should care about these things. And the goal is, again, to give you some new lenses to look through. To promote some innovation and some new insights, perhaps some new questions and some new funding. We'll do these sort of the first Friday of each month of the academic year, and the recordings will be posted on the Institute YouTube channel. If you look up Lyda Hill Institute on YouTube, you'll find the channel easily enough. If you want to know how to do some of these things and other things as well, there will be a couple of week-long summer schools next summer. There'll sort of be a bring your own data situation, although we'll have data for you to work with if you want. And only the sort of one semester introductory graduate statistics are assumed. We're not going to assume anything else. There'll be two sessions. There'll be a session for students, predominantly the trauma track students will get first dibs, and then other graduate students as space is available. That'll be in mid-May, and then there'll be a mid-July, which will be for a more general audience, anybody who wants to come out. So for today, we'll talk about hysteresis and history dependence, because it turns out that's one of the big things that goes on here. We'll look at what are called the elementary catastrophes, and elementary just means they're not the harder type. Doesn't really mean they're elementary. It just means they're not as hard as they could be. We'll talk about recognizing catastrophes, recognizing when you might be seeing a catastrophe at work, even if you hadn't thought about it before. And we'll explore one particular archetype, which is known as the Cusp catastrophe. We'll look at applying catastrophes and catastrophe theory to both data and to creating theories in psychology in the social behavioral sciences. And we'll have a discussion at the end. If you have questions along the way, please raise your hand. I will try to make sure I get a hold of the Q&As and chats and things like that. Maybe a couple of slides before I do it, because sometimes I forget to check frequently. So we'll start with a little demonstration of irreversibility. I like doing kitchen science, and I've done kitchen science for a long time. So here's some kitchen science. What you're looking at here is a brake cable from a bicycle fed through a block of wood and then arcs up and then it connects down in the back. And you're seeing it sort of straight on. So it's hard to see that there's really an arc here. Okay. And what I'm going to do is I'm going to slowly feed this up through the bottom. The other end stays attached and we'll watch what happens. So I start pushing it up a little bit and notice it stays pretty straight, and it stays pretty straight for a while, and it stays pretty straight, and I can pull it back down and try it again. It stays straight, goes up, and it goes up further, up further. You see a little tilt, and eventually, when it gets up near the lower part of the window, it becomes a little unstable. You see the little wobble. And at about this time, a little bit more, and very suddenly, instead of just tilting, it's going to go crashing down. And now, first of all, you should note that it crashed down and how long this is, right? So there's the entire arc. It's fallen over. I'm going to now start pulling it back through the other way, right? I could push a little out more, but I'm going to pull it back through. So you'll notice the arc is getting shorter and shorter, but notice it doesn't pop right back up. Instead, it doesn't pop back up. It starts to pop up here, and it doesn't pop up quickly like the other one did. It does it fairly slowly. Okay? And so by the time it gets back up to where it's essentially straight and going straight up, notice it's a much shorter thing. It's nowhere near up to the bottom of this window. Okay? And so I can pull the rest of it back the way through. So the fun part here is the arc doesn't rise back up at the same length at which it fell over. That is, you can't do forward and backwards on this and expect the same result. In physics, we call this hysteresis in its behavior. And in a hysteresis situation, the process is not reversible. Okay? So, and there's two ways in which it's not reversible. First of all, the reverse doesn't happen at the same length at which the forward happened, right? It fell over after a very long length, but you had to be a relatively shorter length before it popped back up. And then secondly, the falling was very quick, but the return was relatively slow. So if we want to talk about hysteresis, we used what's called Benjamin's machine. The little video we saw was Benjamin's machine, and I've only seen that reference one place. I've never seen another video of it, but there it is. A history dependence in any sort of measurement can produce hysteresis. Okay? That is, the results are not reversible. So you need to know not just the length in this case, what we'll later call an asymmetry parameter, but also the direction in which it's going. Right? You need to know if something's increasing or decreasing. And the difference between there's a difference between hysteresis, where we have multiple what are called branches, and various thresholds, like a step function. If you think about a step function, it's something goes just like a step. And if you just sort of wiggle back and forth along that, you go up and down and up and down and up and down and up and down. Okay. And the sequence of going up and down is independent of the history. If you're here on this side of the step, you're down. And if you're here on this side of the step, you're up. But in hysteresis, you go one way, there's a jump, there's a sudden thing that happens. Notice it suddenly fell over. And then there's a fairly smooth return as you wiggle back and forth. So if you try to come back, it's a fairly smooth thing, and then it's a fairly smooth rise before something else happens. So if you've ever had data that seemed inconsistent to these little wobbles and these little noises, you may have an example of catastrophe. This particular example is known as the fold catastrophe. And it's sort of the simplest of the quote elementary unquote catastrophes. If you were to plot this, it would sort of look like two logistic curves, but offset. So one of the logistic curves is going up, and then there's another one that comes back down. There are 7 of what are called elementary catastrophes. And again, mathematicians call them elementary catastrophes. And to translate from mathematics to normal language, elementary just means I can do it. Doesn't mean you can do it or anybody else can do it. Mathematician who says elementary just means I can do it. But there are 7 that are classified as elementary. 4 of them are called cuspoids, the fold that we've just seen. the cusp, the swallowtail, and the butterfly. And each of these cuspoids has one outcome variable, one dependent variable, and 1 to 4 control parameters or independent variables. The fold has one independent variable, the length, for example, on the bicycle cable. The cusp has 2, the swallowtail has 3, and the butterfly has 4. And our focus today will just be on the cuspoids. The rest of catastrophe theory is really just more math and more variables. Okay, so it doesn't lend you any greater insight into things. It just says, hey, we've got a more funky looking situation. 3 of the elementary ones, the other 3 are called umbilic, and they're known as the wave crest, the hair, and the mushroom. And these each have 2 outcome variables, 2 dependent variables that are used to describe the system, and 3 or 4 control parameters. And then there are the non-elementary, and these are all 5 or more variables. But the best thing to do on this is think about these as combinations of the 7 elementary. So you may have one that is a cusp and a swallowtail and a butterfly put together. And that's going to be 3 dependent variables, and it turns out 9 control parameters. Okay? And so what we do is we investigate them by doing portions. We select variables of the data, and we do that as if they're elementary. And if all those work out, then we'll try putting the non-elementary in. We'll do it all at once. Okay? So this is a classic, and it turns out wrong example. This example is due to Christopher Zeeman, who did a lot of this work back in the 1970s. And this is from a Scientific American article in 1976. So this is the classic cusp catastrophe. And yes, we know it's wrong. And so all of the animal behavior people out there just don't have to yell. Okay, we know it's wrong. We'll just deal with it. But we want to spend a little bit of time on this one. Okay, so first of all, we have what's called a control surface right here. And the control surface has 2 axes on it. In this particular example, we're going to talk about fight or flight. So let's think about a dog. And what is a dog going to do? Okay, so we have an axis of fear, how afraid the dog is, and we have an axis of rage, how angry the dog is. Okay, so we have 2 axes here. And then we have some sort of behavior. And the behavior is going to go from basically flight, from cowering and running away, up through someplace where they're growling, they're attacking, they're being very aggressive. Okay, so that's the control surface, and our independent variables are in the control surface. We also then have a behavior surface, and notice the behavior surface is very strange looking. And this is what catastrophe theory does that's different than, for example, all of your high school mathematics. You may remember from high school mathematics, you had something called the vertical line test. If you take a vertical line, and if it intersects the curve in more than one spot, then it's not a function. Well, turns out this is not a nice smooth function, because if I draw a vertical line, notice it'll intersect 1, 2, potentially 3 places of this curve. Sometimes it only intersects the 1 out here. Sometimes it intersects the 3. Okay? But we have this control or behavior surface up here. And notice these are labeled avoiding or retreating. Is the dog avoiding or retreating? Is the dog growling or attacking? And so the higher up you go on the behavior axis, what's the vertical axis here, the more aggressive the dog is. The lower down you go, the less aggressive and into very passive and running away type thing. So it's a fight or flight situation. Right? Now, one of the first things that we do is this puts fight and flight as being on the same axis, right? They're both behaviors. And so a lot of times in catastrophe theory, people talk about this, and they will talk about things in ways that probably shouldn't. Specifically, they will sort of conflate the qualitative behaviors with a quantitative measure. Okay? One of the things you'll notice down here is this dark line, which is called the bifurcation set. And when you're inside this, so in this region here, you could get multiple different things. So let's look at the path of what happens. Okay? And there are 4 paths that Zeeman put here. If we were to take this path A in the control parameter space or the control surface, notice it's fairly high on the rage, and then the fear happens. So this would be this right here. We would see something up in the control parameter. They projected it up here. As you get more and more afraid, you get a little less aggressive, and then very suddenly you drop down and you can run away. And there's this sudden change, just like there was a sudden fall in the fold. Okay? Likewise, if we go this way, we are avoiding things, but you get more and more angry, and then there's this sudden catastrophe, they call it, the attack catastrophe, and you start attacking. The other thing to note is there are two paths here. And if you follow them, notice at first they stay close together, but then one of them goes this way and one goes this way. And so that's something you will often see in a catastrophe. Last thing is the catastrophe itself is this point right here at the cusp. And that's why we call it the cusp catastrophe, because we have this particular point. We can recognize catastrophe in a lot of ways. One is if you can fit data to it, great. But before you fit the data, there are flags that may be useful that sort of indicate to you you might be looking at a catastrophe system. Gilmore in 1981 noted 7 properties in data that may be indicators. These are not guarantees, but they are the type of thing where if you see 2 or 3 or 4 of these things happening in your data, you may want to take a look. So first one is that data exhibit modality. There are 2 or more stable outcomes for some values of the control parameter or parameters. Right? There's inaccessibility. There's some unstable regions for values of certain values of the control parameters, and these show up as missing regions in your data. So you have data that's everywhere, but there's a hole in it someplace. You see discontinuity. You see sudden jumps in outcome behaviors at certain control values. Now, in order to see this, you've got to see this as a time series data. And so time series data become very important here. Fourth one is divergence. 2 nearby points diverge, and they diverge exponentially, it turns out, over time. We saw those 2 nearby paths that eventually became very separated. Hysteresis, forward and backward aren't the same. There's sort of a stuckness when you try to return to a prior state. There's a divergence of linear response. That is, there's a rapid change in the slope at some point. And then there's something called critical slowing down. If you perturb the system, just nudge it a little bit, how long does it take to go back to where it was? If indeed it does go back to where it was. So let's take a look at each of these on the cusp. First of all, we'll talk about the distributions. A lot of times before you even get into the catastrophe, you'll have a distribution, you'll have a bunch of data, and you can just do a scatter plot and see what's going on. Any of these features may warrant further investigation as catastrophe. If you see dents in your distribution, if you see holes, or if you see notches. Now, any certainty on this requires fairly densely collected data. And these are related to the inaccessibility flag, but because they require such dense data, it's oftentimes hard to see these particular ones. So first of all, the dents, right? If we see data that looks like this, notice there's a little dent in here, and there's a dent here, because a lot of times in scatter plot, we'd expect an ellipse, and this has just been dented in. Okay, so most scatter plots are more elliptical than this. This has some dents. The other thing you can think of as this as being sort of an elliptical distribution like you'd normally see with these tendrils coming out on either end. You can see holes in the data. When you have a situation where I said you have sort of 2 logistic curves, so here's the forward one going up and goes up and then it comes back down at a different point, this will leave a hole right in the middle of the data. So really there's 2 data sets here, one when you're going up and one when you're coming down, but that creates this hole. So if you see holes in your data, you may be seeing this. You may see notches, particularly if your data are very heteroscedastic, right? What happens is, notice there's some variation here, but the variation increases over here, and you get this notch right here at the end where there's nothing. There's no data. This figure happens to be from something that Lauren Cobb did back in 1981. So we'll talk about the cusp, that fight or flight, as sort of the archetype of a catastrophe. The cusp has 2 parameters in the control space. It's got asymmetry, which we always call A, and bifurcation B. Unfortunately, they call asymmetry and bifurcation A and B. Unfortunately, they call later bias C, and they call second catastrophe D. So the sort of alphabetical thing wears off pretty quickly. The bifurcation parameter, in some sense, is a moderator, but not quite a moderator, of the asymmetry. At small values of the bifurcation parameter, there's no hysteresis. You can go forward and backwards. There's gradual changes. Everything works out as normal. But at larger values of this bifurcation parameter, you see the hysteresis. And notice the amount of hysteresis due to a change in the asymmetry parameter depends upon the value of the bifurcation parameter. So we'd like to think of the bifurcation parameter as moderating the asymmetry parameter, but that's really not the whole story, right? A moderator in statistics is something particular. This kind of sort of is like a moderator, except it's the nonlinear version. However, normally you need to rotate your variable axis to get to these control parameters. And I'll show you the example here with the fight or flight. So now we're back to this fight or flight, and we had the fear and the rage axes, but the bifurcation axis comes straight out here, okay, and comes straight out and through that cusp point. And the asymmetry axis then is perpendicular to that. So in some sense, we've taken the fear and rage axes and we've rotated them 45 degrees. And whether you rotate clockwise or counterclockwise is anybody's guess until you start thinking about it carefully. Let's see here. There is a hand somehow, and let's see if I can get to the hand. Somebody's raised a hand, but I can't. So I can't hear you, but if you put something in the chat or the Q&A, I should be able to get to it, okay? Not letting me do this, obviously. So I'm sorry, you'll have to put it, Jen, in chat or the Q&A, and I should be able to get to it then. So, yep. When we see this sort of behavior, then notice you're going to have to change your axes, okay? And so oftentimes the axes we work with in theory aren't the axes we want to work with in terms of A and B. Well, you've probably done something with factor analysis or PCA or things like that. So actually you're used to doing this, okay? And the good part is you can then work with numbers and variables that make sense theoretically, and then we can just transform them in order to pick off what we need to do for the analyses. So the modality flag shows up in the Cusp catastrophe. And there are multiple modes in the shaded region of the control parameters in this right here. And the modality was you have multiple modes. So anytime you have control parameters in here, they may be right here, they may be up here. Turns out it's possible to be here, but this is unstable. And so it's very incredibly unlikely that you'll find the values here. Okay? But you see modality, you see two or more stable regions. So for these control parameters, you could be here or you could be here. That is, you could be cowering or you could be growling. The inaccessibility flag is related to that. You could be in this region here, but it turns out this region is unstable. And so it's not easy for somebody to stay in there. And therefore, what you see is just what's going on here. Okay? You're not going to actually find people in here. You're not going to find any data in here. If you take enough data, yes, you will occasionally see something in here, but this is going to be like generally less than 0.1% of your data. So if you have 1,000 data points, you might see one in an inaccessible region. Okay? The discontinuity flag that Gilmore talked about is when you have some of these jumps. And notice there are two places here you could have a jump. One is if you have something which is slowly increasing, right, getting more fearful, does this until some point it just snaps and it jumps up here. And likewise, if you have a dog that's getting, sorry, it said getting more angry, and this one's getting more fearful, then all of a sudden you have this sudden drop. And it's tough to talk about fight, flight, and fear and anger because notice, again, these axes are not exactly in the right direction. But it is true, if I follow something where I'm getting more and more and more angry, eventually I snap and I jump up. And likewise, if I follow something parallel to that fear axis, eventually I jump down. The divergence flag says that two nearby points could separate. And again, you need time series data for this. But they've drawn these two paths here. Here are two paths that the control parameters are very close together, but their behavior over time is much different. This dog ends up running away, whereas this dog ends up attacking something, even though they started very close together. If you don't have time series data, you don't have this sense of nearby points separating. You just have nearby points or not nearby points. And hysteresis, which also requires time series data, says that forward and backwards not the same. And we can do this by looking at the following. If I were to take growling and say, let's get more and more and more afraid. And so we've run over here, and then there's the flight catastrophe, but then let's get less and less and less afraid. So I get less and less and less afraid. Notice I don't follow exactly the same behavior back. That is, I don't start growling again right here. I have to get all the way over here and jump up before I start growling again. Okay, so forward and backwards aren't the same. So again, if we were to just follow this path in the control surface forward and backwards, we'd see something that was much different. It doesn't drop down and it starts running here, but it doesn't start growling again until it gets over here. The divergence of linear response says that you'll get a change in the slope. That is a big change in the response variable divided by a small change in the control parameters. So that is for growling, if you think about the slope here, right, how steep it is, notice it's fairly shallow here, but then as you get near this curve, it starts to really drop off, and then boom, right before it falls off the cliff, you have a very steep slope. And likewise, going the other way, right before falling off the cliff in the upwards direction, right, you get right here, and then you get almost vertical, and then you have to just jump up. Right? And so we see some of these types of things. The cusp, unfortunately, doesn't really show the critical slowing down flag. This still requires time series data, but you don't see it that much. And really, it's not something that it's a good flag for the cusp. It is for some of the other catastrophes. So the catastrophes, we looked at the cusp a lot. We looked at the fold very briefly. The fold has one control parameter. It's just got an asymmetry parameter. That would have been the length in my demonstration. Okay, but it has two stable areas. Notice it has the stable area of pointing straight up and has the stable area of laying down on the counter. The cusp typically has two control parameters, the asymmetry parameter and the bifurcation parameter. It's got two stable areas and an unstable area. The swallowtail has three control parameters, asymmetry, bifurcation, and we call the third one bias. It has two stable and two unstable areas. And so you'll typically have two holes in your data. The bias, which is also called the second asymmetry variable, really, it just creates a more complex behavior surface. Okay, and it's difficult to visualize because now that we have four parameters in total, three independent variables and a dependent variable, it's hard to plot anything. And so very quickly people say, okay, we can't do this. We could look at a slice of this, but we can't look at all of it. And the butterfly has four control parameters. It has asymmetry, bifurcation, the bias, and it has a second bifurcation. And so it ends up with three stable and two unstable areas. But one of the things that this can have is an oscillation like the step function. And so we said that, the hysteresis was different than the step because of the inability of it to oscillate the same way. The second bifurcation variable, though, creates multiple jump paths. You could go from the first stable to the third stable or the first to the second and so on. And you can also do things like go then very quickly first to second back to first. So sometimes there's hysteresis in a butterfly and sometimes not. And again, this will be difficult to visualize because now we have 5 dimensions, 4 independent parameters, 4 independent variables, and the dependent variable. So if we want to apply complexity or catastrophe to the data collection, there are 3 approaches to the type of data that you would need. And I've listed these 3 from the hardest to the easiest to acquire. The first is that you have multiple time series trajectories. Okay? The second is that you have cross-sectional data at 2 points in time. And the third is that you have cross-sectional data at 1 point in time. And in some sense, the 1 point in time is perhaps easiest to acquire because you just survey people. Cross-sectional says you have to survey, but you got to have a matched survey if you want the 2 points in time. And multiple time series trajectories means you've got to survey people many, many times and many people. As usual, the question that gets asked, how frequently is frequent enough? That is, how many time series points do I need? Is difficult to answer. Psychology as a rule doesn't have a good handle on characteristic times, right? We know that people typically don't get, quote, well, unquote, during therapy overnight. But is it over a week, 10 weeks, 10 months, 10 years? We're not really sure necessarily. So this is a difficult question to answer. The guidance I would give you is get as much data as you practically can. Okay? The more data you have, the better chance you have of seeing what's going on and working with the theory. So trajectory data, that is the time series data. Time series, it's the gold standard. It's always the gold standard when you deal with dynamical systems. Plus 5 of the 7 flags that Gilmore proposed require time series data. So get time series data. That's the big takeaway for the data. Really what you want to do is you can think about each trajectory as being a thread in the cloth of the response or the behavior surface. And the more threads you have, the better your chances are of seeing what the surface really looks like. Okay? And so having time series gives you some sort of global information about each trajectory. You could say, oh, this dog started at sort of a quiescent state. It was just laying there. And then something happened to make it a little more afraid. And then it got to be a little bit more angry. And then it got to be more afraid and more afraid and more afraid and more afraid. And then this happened. Right? You want to get as much data as you can. And again, how much data? Well, you want to sample frequently enough so that the consecutive samples show small movements on the control surface. You don't want to jump from one side to the other side. You want to get it along the way. So no big jumps, and you don't want things that show too much stationarity, right? If you have a sleeping dog, for example, and the sleeping dog is there, and you measure the sleeping dog, they're not afraid, they're not angry. And you measure a sleeping dog again, they're still not afraid, they're still not angry. And you measure them again, they're still not afraid, not angry. If you get a lot of stationarity, you're not going to get threads, right? We just get a little point, and we need the threads. So what variables? Well, theory should help some, but that's really a good question as to what variables you would need. And we'll talk about the variables shortly. So the 2 time point data, for example, you could say, oh, I'll get pre and post intervention data. That's probably too large a time gap, but I really don't know. It depends on a lot of things. Chip and Knight and some others published a paper a couple of years ago where they used data from basically baseline and 6 months, and it worked out reasonably well. You should know there's some debate about this approach, and frankly, the more I look into it, although the 2 points approach has yielded a lot of insight, it's on incredibly shaky ground from a mathematical point of view. I mean, it's just the mathematics behind it are really not that solid. However, as Dave Pincus often reminds me, he's not a mathematician, he's a psychologist. What he wants is insight. And to the extent that it's produced insight, it should be used. Okay? The claim from the adherents is 2 points are enough to show the direction of movement. So you know whether you're going, for example, to the left or to the right. And this gives you local information about the trajectory, which is often enough for something like a cusp or a fold. Right? If we know how much of that brake cable is pushed through, and we know whether I'm shortening it or lengthening it, you can tell me whether it's going to be laying down or standing up. Okay? So we use 1 point essentially to put the surface there, and we put the other one on the direction to know whether I'm on this stable part or that stable part. Okay? So I'm a little bit concerned sometimes about this from a mathematical viewpoint, but from a pragmatic viewpoint, it works very well. And this is probably the place most people go because it's relatively easy to get 2 points in time, especially 2 points that aren't too far apart. Lastly, you can do cross-sectional data. And this requires an assumption about mixing, something called ergodicity. It's probably not a terrible assumption to make. However, because you don't have any knowledge, either local as you do with the 2 points or global as you do with the time series about the trajectories, you really are making the big assumption that all the trajectories that lie on the behavior, that all data points are on trajectories that lie on the behavior surface. And so you're sort of assuming your conclusion. Instead of looking to see if it's there, you're making the assumption so that you can do the fitting. It's a little bit tricky, but it's not too terrible because most things are mixing, as they call it. So you have a less complete connection or less complete knowledge of the connection between the response surface than the data than you do in the time series case. Again, this has been used on several occasions for things, and it works out well enough. Okay, so the pragmatist says, go ahead and do it. There are some controversies you should know about, and there are 2 in particular. The first controversy was basically overselling. Back in the 70s, and part of it was Christopher Zeeman, but a little bit Rene Thom, who was the mathematician underneath all of this stuff, did a lot of things. And Arnold, who was a Russian mathematician and one of the top mathematicians of the 20th century, who did work in catastrophe theory, said in his book, it was claimed that the new science, catastrophe theory, is much more valuable to mankind than mathematical analysis. Well, the mathematical analysis he's talking about is Newton's calculus and Newton's physics. And so to claim that something is more important than the basis of all of engineering and also the basis of most of our statistical analyses, right? Because we use calculus underneath all of our statistical methods. Yeah, that might have been just a little bit too much. It was certainly not a way to win friends and influence people. And this has been largely resolved. The math is solid, and some of the applications are really solid. The hype, yeah, not so much. Okay, so know that if anybody says anything, yeah, there was a controversy in the late 70s. We've sort of moved beyond that one. The second controversy, though, has to do with the data streams and the analysis. Can you do catastrophe theory without time series, or must you have time series? It's all about the response surface, and that's what the catastrophe theory, the mathematics of it is. It says nothing at all about data collection. Okay, so you go with it, and the pragmatist says, sure, we can do this. Mathematicians say it's not really there. The other thing is that all of this relies on what are known as potentials, and whether psychological variables obey the mathematics of potentials, like say energy does in physics, is an open question, and whether or not they should is an open question, but people use a lot of the physics approaches. This one's largely unresolved. However, people have had success fitting data. Okay, so you keep a little bit of a grain of salt when you're thinking about this one, but yeah, it works out. Okay, and because it works out, we use it. So let's talk about, instead of the data and the data collection, let's talk about theorizing. Because without theory, the search for control parameters can be insanely difficult. We have no idea what asymmetry is just in general, and no general bifurcation or bias or anything like this. So let's look a little bit at what each of these do so that we can think about how to connect some of this to theory. So first of all, we can talk about the asymmetry. You get an asymmetry parameter anytime you find that there's a behavior that is different above or below some threshold. And this is what we think of sometimes as, it's inconsistent. Most of the time the data is down here, but occasionally it's up there. If you see something like this, you see a dependent variable that looks inconsistent compared to an independent variable, you may be looking at an asymmetry factor, right? So you've got two different behaviors depending upon where it is. This may seem like a trigger, but again, it's got to be a history-dependent trigger. So this requires you knowing a little bit about the state of the system, the behavior of the system at whatever the previous time is, whatever that happens to be. This usually acts in conjunction with the bifurcation parameter. You could use the fold. There are lots of things where you just get an irreversible behavior, right? You're moving forward, the bicycle cable falls over, you back up, you back up, you back up, you back up, and finally it raises up. There are some things where the irreversibility is probably very difficult to do. Take a kid who doesn't know how to read, and you give them enough practice and over time, and they know how to read. That's a very different behavior. Try to get them to unlearn how to read. Short of some fairly traumatic brain injuries and things like that, it's difficult to do. But you can see an example of asymmetry in the cusp. Guastello, and Steve Guastello has done a lot of the work on catastrophes, particularly in psychology. He's also done a little bit of the mathematical stuff. I'm not always in agreement with him, but he's been successful. So you can take that for whatever you want. He looked at bus accidents and he used transit hazards as the asymmetry and stress as the bifurcation. At very low stress, there's a smooth increase in the number of accidents as a function of the number of hazards, right? The more difficult things are, the more accidents you have. But at high stress, people who are under high stress, they tend to snap. That is, you get a smooth increase in the number of accidents as the number of hazards goes up. And then at some point, it just snaps. And instead of having a smooth increase, all of a sudden you have a gazillion of these things. Okay? Now, these data were mostly cross-sectional, and they assumed that people are going from low stress to high stress. They kind of ignored the inaccessible region. Okay, it's not clear that the inaccessible region was really dealt with clearly. The ideas of there being multiple stable regions and an unstable region. So it's a little bit iffy. But still, there was a certain amount. This makes a certain amount of sense from just a layperson's perspective. And Guastello was able to back some of this stuff up. There was a little back and forth in the literature over this particular one that either he came out on top or the other side just decided it was not worth their time and they moved on. You can interpret it whichever way you choose. The bifurcation parameter is one that impacts another control variable by more widely separating the outcome states that the other variable predicts. So it's not exactly a moderation. It's not a linear effect for one thing. And for very low or very high values of asymmetry, it changes the slope associated with the asymmetry, right? But it doesn't really separate outcome states, right? If you're at a high enough level of fear, it doesn't matter how angry you are, you're just running away, right? And so it's really when you have these medium values of the asymmetry parameter, it introduces a discontinuity in outcomes as the asymmetry changes. So one example happened to be from Chen. It was a nursing study. The outcome was grip strength, and they were looking at whether grip strength was impaired or normal in older people. The asymmetry was inflammation, right? Whether it be due to arthritis or anything else, they measured a particular chemical, interleukin-6, that is known to go with inflammation. And inflammation always was a very inconsistent predictor in previous studies. Notice there's a modality flag. You got an inconsistent predictor. And so they looked at it and said, if we look at this in conjunction with bifurcation parameter, which they used executive functioning as the bifurcation parameter, they found out that a Cusp model fit very, very nicely, right? And so a lot of times, previously inconsistent data with the addition of a bifurcation parameter starts to make more sense. The bias in something changes the shape of the bifurcation set. If you remember, in the original bifurcation set with the cusp, we saw was just a little sort of triangle shape. Here, if we're looking along the increase of the bifurcation parameters in this downward direction, here's the bifurcation set that we saw with the cusp. The bias adds essentially a little triangle above this. And so that now there's these 3 points. This is sort of a curve. So there's this point here, and a point here. And so the change of your bifurcation set shape is what tips things off to this. Now, this is needed sometimes when you have some behaviors that seem to, and again, time series data that seem to go A, B, A, whatever those are, while others go A, B, C when you increase the asymmetry. Right? So if sometimes you see one pattern and sometimes you see another pattern, you may want to be thinking about a swallowtail, something that's got bias. Right? Most of the examples of the swallowtail are in optics. It turns out optics are just all about this sort of swallowtail catastrophe. The one that you're probably most familiar with is that a rainbow is effectively a swallowtail catastrophe. Okay, so you see them all the time, but there are some other things where it's much, much more so. Guastello, again, 2010, did something like this. He had people play a game simulation where they were simulating how they were going to respond to an urban catastrophe, okay, in response. The asymmetry was how competitive the participants were and how competitive the participation was. The bifurcation variable turned out to be group size. And then the bias turned out to be the group performance. These 3 taken together would predict what type of response they would have. Would they have oh yeah, it's not a problem, so we'll just ignore it. We're not going to call out the troops, as it were. Or, oh my God, it's a terrible thing and we have to call out something. We've got to get it going. The fourth one, here we go, is the second bifurcation, and it allows for an even more complicated surface. Okay? One example, it was something that Guastello again did back in 1985. And notice, right, 35 years ago, people were doing this. The outcome was exam scores in an introductory psych class. And basically there were 3 modes: students who failed or dropped, students who, yeah, they were kind of mediocre, and then those outstanding students. Okay? The asymmetry parameter happened to be ability, and this was measured by prior psych courses or the number of semesters in college they had. The bifurcation parameter was the perception of the course and whether it was considered to be important for their career goals or not. Okay. The bias was their intrinsic motivation, and they measured that by what was the major. Okay. And this, it wasn't clear in the paper like this. I thought about asking Steve about it, but decided it wasn't that important just yet. And then the second bifurcation was the course iteration. The course had been taught 4 or 5 times, and so how many times had it previously been taught? 0 times, 1 time, and so on. Okay, and these turned out to be very good predictors of exam scores using a butterfly catastrophe. So, having said all of that, I'm going to stop the sharing, and we can chat a little bit about this. If you have questions, and put them in the chat or the Q&A. I've got to see. I guess I can't turn on from the webinar to let everybody just talk. So we'll have to go with that. Let's see if there's anything there. So if you have questions, please drop them in a chat or drop them in the Q&A, and we'll take care of those things as we can. Okay, then seeing no questions, I want to thank you all for showing up. We'll do this again in a couple months. We'll start working again in February on this. And I hope you have a good end of the semester and good holiday break. And we'll see you, I guess, in the new year. You take care.